Hello everybody. In this video we'll talk about different applications of vectors. The one we will focus on in this particular video is going to be on ramps. That's like things like, dogs on ramps coming out of the back of a car. Okay, so first of all, just a reminder from dynamics or forces, some key points. Okay, so whenever we have, we won't always need to deal with forces with things on ramps. Sometimes things are just kinematics problems where we don't need to consider forces, but when we do, we want to make sure that we are drawing an accurate free body diagram. Okay, we want to, in this case, moving forward, we're going to now label our force components with arrows. So we'll break our forces up into components, which will be more useful to us. Okay, and then when we apply our Newton's second law, our F net equals ma, just a reminder, things that are vectors in this formula, force and acceleration are vectors. So we want to make sure that we're using numbers that are acting in the same direction. Okay, so we've seen this table before for forces, which are pretty common to us. And I've highlighted some that I just want to focus on, that being force of gravity is mass times gravitational strength, or 9.8 meters per second squared. Okay, so force of friction is equal to mu times Fn. So that's something that depends only on normal force. The friction force is always going to oppose or be opposite to the direction of motion. Okay, and our normal force is always going to act perpendicular to the surface, and those things are going to come into play in a couple slides here. Okay, so on ramps, we have a portion of the force of gravity that is going to accelerate the block down the ramp. We'll see this slide again, so I'm just going to go and I'm going to put a theta in here. I picked this off the internet, and that is a search that you can do. I just went and looked for block on a ramp free body diagram, and if you'd like, you can go take a look at different ways that people show those three free body diagrams. This is one that I'll refer to. So I'm going to change that 30 degrees to theta, though, because really the angle of this ramp could be anything. Okay, and just a reminder, our Fg is just our mass times 9.8. So if we have mass, we've got force of gravity. If we've got force of gravity, we can find the mass. The other one is Fg is also the same as weight. So if we ever see, hey, the weight of an object is 620 newtons, well, that just is also another equivalent word is the force of gravity for that object. Okay, so with ramps, we don't always need to apply forces. Let's look at a general case where we've got an object. In this case, I'll just draw a ball. We know that if we put a ball on a ramp that is angled at some angle theta, it is going to accelerate down the ramp. Okay, so the amount of acceleration is going to be some portion of gravity. So we can look at that portion as looking at how the height of the ramp or the vertical drop of the ramp compares with the overall length of it, or the length that this ball is going to be rolling down. Okay, so if we're looking at acceleration, the portion of gravity is going to be the height of the ramp or the vertical drop as it compares to the overall distance along it. Be some fraction of gravity. Okay, another thing to note here is that h over d in this triangle is just sine theta. So acceleration is going to be g times sine theta down a ramp. And I'm going to switch colors and put a box around this because we'll come back to this formula in later questions. Okay, so next, when we do have a force question, what we're going to do is we're going to break this gravity force into its individual parts. And right now I'm going to skip over to an applet that is a FET applet where we have a dog. And if I push this dog up the ramp a little bit, here's the dog just sitting on the ramp. If you want to go and play around with this, you can Google FET ramp forces in motion. On this diagram, it shows us neatly the three forces that we have in our slideshow, so I'm showing you that, hey, I'm not making this up. This force of friction, the force of friction that is holding this dog on the ramp is just going to be equal to the portion of gravity that's trying to push the dog down the ramp. Okay, so I just want us to keep that in mind. I'm going to break gravity into its two parts, and the two parts of gravity are going to end up being equal to our normal force because we are not accelerating in the up and down direction, or the other component of gravity acting down the ramp or parallel to the ramp is going to be equal to our force of friction. And when those two things are equal, hey, look, our dog doesn't go anywhere. Okay, so we've all walked up and down a ramp and stood on a hill. We know that we can do that. So a couple of key points here. So the portion of gravity that is acting down the ramp is F parallel. Now I'm going to go down to my gravity force and I'm just going to draw the individual components. And really what I'm going to do is I'm going to draw the components of gravity that are acting in the direction that we care about. And the direction that we care about is going to be down the ramp, and perpendicular to the ramp. So I'm just resolving this gravity force into its two components. Now the two ways that we talk about this is, or this little symbol here, this little two lines, that just means parallel to. So the force that is parallel to the ramp or acting down the ramp is equal to the portion of gravity, or Fg, times the sine of theta. Okay, we could do some geometry, and with some geometry we know that this is also angle theta in here. So this angle theta, our parallel force, is opposite to theta, and that's where our sine ratio comes from. The other ramp, or the other portion of the gravity force that's acting perpendicular to the ramp is F perpendicular. So I'm just going to point up to that line. That just means perpendicular, or at 90 degrees to the ramp. On this one, I forgot to write it in. That symbol just means parallel. So when we see those things, it's we just need to remember, hey, that F parallel, that just means that it's the portion of gravity that's acting down the ramp. When we see the upside down T, that is going to be our portion of gravity that's acting perpendicular to the ramp. And that's going to be important when we start looking at friction and normal force. Okay, so a couple things to point out here. In this diagram, our normal force is going to be equal to that perpendicular force acting down the ramp. Okay, our parallel force is going to be equal to our friction force. Okay, so this is when object is, sorry, I'm going to bring this down here, stationary or not moving. When the object is not moving, those forces in the parallel and perpendicular direction have to be equal. Otherwise, this object would be moving and it would be accelerating. It'd be speeding up or slowing down. Okay, so let's actually apply that to an example. Okay, so here we have a car that starts from rest and coasts down a 5-meter high ramp that is 18 meters long. Okay, so as per usual, we will draw a diagram. This is a 5-meter high ramp, and it's a car. So I should probably draw a car, some people in it having some fun. Okay, they're going down a ramp that is 5 meters high and it is 18 meters long. So the length of this ramp is 18 meters. Okay, I want to find VF. Okay, so there's no mention of forces here, so this is a kinematics problem, and with our kinematics problems, we are going to just apply our VFDAT. Okay, so this car starts from rest. This car starts from rest, so our VI is 0. Our final velocity is what we're looking for. The distance that this car is going to roll is 18 meters down the hill. The acceleration is going to be something that we can find. Our acceleration is just going to be the portion of gravity that is g times h over d, or 9.8 times height over distance down the hill. Okay, if we plug and chug that, we should get that our acceleration down the ramp is 2.7 meters per second squared. We don't need time, so we'll just cross that off. Okay, so now I need to go to my formula sheet and figure out which formula uses VI, VF, D, and A. That formula is VF squared minus VI squared is equal to 2AD. VI is 0. Okay, and then we'll plug and chug some numbers. Okay, we should get that VF squared is equal to 97.99. If we take the square root of both sides, we'll get VF is equal to 9.9 meters per second. Okay. Okay, so we found VF. This car is going to speed up down the hill or accelerate down the hill, and we're looking for the VF at the bottom of it. Okay, example number 2. If we have a ramp that has a length of 2.1 meters and a height of 0.1245, the object starts from rest, and after traveling 160 centimeters, it reaches a velocity of 1.362 meters per second. Find G. So we're actually going to find what our gravitational field strength is. Okay, whoops. Okay, so this is another question where it's a kinematics question. Ooh, that's kind of not a very good triangle. Let's try that again. Kinematics question where we have a height of 0.1245 meters to 0.10 meters. Okay, the object starts from rest. So again, we'll write out our VFDAT. Okay, so in this question, we're given that our final velocity is 1.362 meters per second. Okay, our travels 160 centimeters or 1.6 meters down this hill. Okay, so then we can look at our one of our formulas and we can go and find what the acceleration of this object is down the ramp. Okay, we don't need time. Here's our object O. Okay, so we can use that same formula that we used before, where VF squared, minus VI squared is equal to 2AD. Okay, so VF is 1.362, VI is 0, 2A times D is 1.6. Okay, so I can plug and chug for this and find that my acceleration of this object will be 0.5797 meters per second squared. Okay, so I found how fast this thing is going to accelerate down this 2.1 meter ramp. Okay, so what we're asked to find is we need to find G, or gravitational field strength. So I'm going to go back to our acceleration formula, and that is just acceleration is a portion of gravity. Okay, and then we'll go and plug and chug the numbers that we have. We know that this thing is going to accelerate 5.97. We know that the height is going to be 0.1245. 0.1245 over that distance of 2.1. Okay, now we can go and plug and chug for what G is going to be, and we can plug and chug a number of 9.78 meters per second squared. Okay. Okay, next, if we have, now we have an example where we have forces that are involved. So if we have a 562 Newton object that is on a frictionless inclined plane, so here's a inclined plane at 30 degrees. We've got an object that is like so. and it's a 562 Newton object. So that's going to be the weight of this object. So I'm going to draw this force of gravity, or weight, is equal to 562 newtons. Okay, what is the mass of the object, and then what is the acceleration of the trunk down the ramp? So there is another force that I need to draw on my free body diagram, and that's going to be my normal force. I'm going to draw that nice and long so I can put my label up here. Our normal force is going to be acting perpendicular to the ramp. Okay, so again, I've kind of tilted, my axes, and thinking that my axes are now pointing down the ramp and perpendicular to the ramp. Okay, so my mass of the object, I know that Fg is equal to mg, so if I want to find mass, I can take the force of gravity divided by 9.80, and in our case, our numbers are 562 newtons divided by 9.8 newtons per kilogram. The mass of this object to be 57.3 kilograms. Okay. Okay, question B, if I'm asked for the acceleration of the trunk down the ramp. So acceleration of the trunk down the ramp is going to be where we are applying our F net is equal to mass times acceleration. Okay, so this trunk, the components of gravity for this trunk are going to look like that parallel force. Here's our perpendicular force. So the only force that's acting down the ramp that is going to accelerate this object is going to be that force that's parallel, or acting down the ramp. It's going to accelerate some mass with some acceleration. Okay, so our force parallel is going to be that gravity force, that portion of gravity force when I take the sine theta of it. Okay, my force of gravity is just m times g times the sine of theta. And I'm leaving my variables all in here because I'm going to get to a point where I can cancel out my mass on both sides. And I'm going to find that my acceleration is equal to g sine theta. Okay, so in theory, in the perfect physics world, no friction, no friction at all. Any object is going to accelerate down a ramp with the same acceleration, regardless of its mass. Okay, so and that's similar to acceleration due to gravity. Things that are falling in free fall are going to fall with an acceleration of 9.8 meters per second squared. Doesn't matter the mass. And this is again in the perfect physics world with no friction, which, as we all know, doesn't really exist, but that's okay. Helps for our analysis. Okay, so the acceleration of this object down the ramp will be 9.8 times sine of 30. That is going to be 4.9 meters per second squared. Okay. So what about the situation where we have friction? What coefficient of friction is needed to keep that object stationary on the ramp? So this is just an extension of the last question. Okay, so I'm going to draw this ramp again. It's at an angle of 30 degrees. Okay, I'm going to have my object. Okay, our free body diagram, or the forces, the forces that are going to be acting on this thing. We'll have our portion. So instead of drawing, in fact, I will draw this and then erase it. So this is our gravity force, Fg. And our Fg on this thing will be 562 newtons. Okay, so instead of drawing that gravity force, I'm going to draw the components of that gravity force only. So here's going to be our F parallel, which is our gravity force. Sorry guys, maybe we'll start with that. It's our gravity force times the sine of theta, or mg sine theta. Okay, the portion of this that is acting perpendicular to the ramp. Okay, I'm just going to go and move this perpendicular force over so it's actually acting on the object. That perpendicular component of force, or the force that's pushing this block into the ramp, is Fg cosine theta. Okay, now I'm going to go and just get rid of a couple of things on here, like the force of gravity. I'm going to get rid of this arrow, the force of gravity, because we've drawn the components of it. I'm going to get rid of this perpendicular force because I've drawn it over so the tail of that thing is actually acting on the block. Okay, a couple other forces to draw is our normal force. That's an arrow. This is our normal force. Okay, and then we'll also have the force of friction. It's acting on here. So if the object is stationary, acceleration is 0. Okay, so that means that our normal force and our perpendicular force have to be the same. Okay, it also means that our parallel force, or our force that's acting down the ramp, has to be equal to friction. Okay, so I'm going to first apply my force of friction is equal to mu Fn. That's a formula that's on our formula sheet. We are looking for this coefficient of friction. So before we do that, use this formula, we're going to need to know what our normal force is. Okay, so our normal force is going to be equal to, our normal force will end up being equal to our perpendicular force. Because, and if I back up one step here, guys, like all I'm doing is I'm applying F net is equal to ma in the perpendicular direction. In the perpendicular direction, our acceleration is 0. So that means that our, sorry, you'll have to excuse me, I'm going to erase this and we'll come back to that. That means that if we look at, hey, our Fn, or our normal force, subtracting our perpendicular force, that has to be equal to 0. Or our normal force has to be equal to our perpendicular force. And our perpendicular force is just Fg times the cosine theta. And we know what Fg is. It's 562 cosine of 30 degrees. If I multiply those together, we'll get 486 newtons for a normal force. Okay, we also know that our friction force has to be equal to our parallel force because this thing is stationary. It's not moving. So that means that our force of friction is going to be equal to Fg times the sine of theta, or 562 times the sine of 30 degrees. So our force of friction in this case is going to be equal to 280. Oh, I don't know why that won't go away. 281 newtons. Okay, so now I'm going to go back to this original equation. 281 newtons is our force of friction times mu Fn. And if I plug and chug, I should get mu is equal to 0.577. Okay, so can you please give this question a read and the questions on your screen a try? Okay, then can you please go and try chapter 4, worksheet number 1, ramps, questions 1 to 9. Thanks, ladies and gentlemen, and we'll see you again soon.